All right. Today we are going to do something really important with vectors. So we've talked about what happens if you have vectors that are either up and down or side to side, but they're all in the same, along the same line. What happens when we have a vector that's slanty? So for example, let's say I have a box sitting on the ground here, and there is a pulley with a rope over it. So there's my pulley, there's the rope, and here's a guy standing there tugging on the pulley. If we were pulling directly up on this box, we know the box would lift. If we were pulling directly sideways, we know the box would slide, but we're actually pulling it at an angle. So what we're looking at here is a force vector. A force is a push or a pull, and we're looking at that vector as being at an angle. So in vector problems, most of the time you know the magnitude and the direction of the force vector that you're working with. So let's say that this guy was holding onto a force sensor or a scale, and it told him that he's pulling with 50 pounds of force. And then we took a protractor or a level and we measured and discovered that the angle between the horizon and that pull on that thread there is 30 degrees. What's really important about this is that the pull isn't entirely upwards and it isn't entirely to the right. It's a little bit of both. Part of it is to the right and part of it is upwards. And if you were to zoom in on that, you would notice that what I've just drawn is a right triangle. And so there's some interesting math that goes along with right triangles to help us solve this. So before I dive into that, for those of you who either have forgotten geometry or haven't taken it in a while, let's sort of draw a right triangle and talk about some vocabulary that goes with it. So here is a triangle. I have a nice right angle right there, that's 90 degrees. And in my vector problem, I'm always going to know this long slanty side because it's the one that is sitting there at an angle. So first and foremost, we call the stick parts that are at 90 degrees from each other of a right triangle the legs of the triangle. And then you can always find the slanty part because it's opposite the right angle. We call that slanty part the hypotenuse. And then the legs of this triangle, one of them is sideways and one of them is up and down. And if you think about your vector coordinate system, actually the graphing coordinate system that we've all known for math forever, if you have ever graphed something, you know that that's the origin. And you have up and down, which we call y, and we have side to side, which we call x. We're going to continue with that here. And if it's a sideways line, we're going to call it x. And if it's a vertical line, we're going to call it y. Now, when we add an angle into this, because I only know in my problem, I only know the hypotenuse and this angle. I have no idea how much x or y are. And it turns out that I can figure out what x and y are as long as I know what this angle is. And for the record, when I draw an angle, I will often use this symbol right there. It's the Greek letter theta, and it looks like a zero with a line through the middle of it, or an egg that's drawn in half. And that is just to refer to a particular angle that's not the right angle in a right triangle. So that's just an angle. And it happens to be the one that the problem gave us. Now, when we look at this angle, we can determine that one of these legs of my triangle is right next door and the other is opposite it. Opposite it like it's going to get eaten right here. The opposite side, in this case, is y. And in this case, right next door to it, x, we call that adjacent. It's worth knowing that you can draw a right triangle the other way. If I had been given this angle in the problem, then this would be the opposite and that would be the adjacent. But for the problem that we just drew right now, compared to this angle, y is opposite that angle and x is next door or adjacent to it. And that is going to be really important because there are things called trig functions, trigonometry, that relate this angle to two of the three sides of the triangle. And I'm going to write them out, and then we're going to do a little bit of algebra, but I'm going to do this quickly so that I don't bore you to death if you've already had this or if it's over your head, because it turns out you don't need to know too much about this to be able to use this. So, according to trig, the sine of any angle is equal to the length of its opposite side divided by the hypotenuse, which I'm going to abbreviate. The cosine of any angle is equal to the length of the adjacent side over the hypotenuse. And there's a third one, which we're not going to use today, but we will get to eventually, called tangent. The tangent of any angle is equal to the opposite side, the length of the opposite side, divided by the length of the adjacent side. And you will often hear these trig functions referred to with the remembering or mnemonic device called SOHCAHTOA. Every math teacher who's ever taught geometry has probably used the word SOHCAHTOA to remind you of these trig functions. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So that's how we remember them. So for the purpose of today's math, I'm going to simplify these two guys here a little bit further, because it turns out that in this problem, I'm always going to know the hypotenuse, and I'm always going to know the angle. So I'm going to know this, and I'm going to know this, which means I can solve and figure out what the opposite and the adjacent, or the x and the y, are here. So all I'm going to do is a little bit of algebra to rearrange these guys so that they're a little easier for us to use and we don't have to do as much algebra in our problem. So algebra says if I write this problem out as a fraction, opposite over hypotenuse, how do I get opposite all by itself? Because that's my unknown. How do I get it by itself? Well, algebra says that if I am taking something and dividing it, to get it by itself, I have to do the opposite. I have to multiply both sides by the hypotenuse. That will make this cancel, and then we are left with the equation. The hypotenuse times the sine of the angle is equal to the opposite. I'm just going to rewrite that this way. Opposite, the length of the opposite side is equal to the hypotenuse times the sine of the angle. And I could repeat that math, but I won't bore you with it. The same exact thing is true with cosine, except it's adjacent. The adjacent angle is equal to the hypotenuse times the sine of the angle. Okay, because I'm always going to know the angle and I'm always going to know the hypotenuse. So with that in mind right there, with these two things in mind, let's go ahead and figure out how much of that 50-pound pull is to the right and how much of it is upwards. So I'm going to redraw my triangle here, putting in my numbers. 50 pounds. And then here is my sideways part, here is my vertical part, and this is 30 degrees. A question that students sometimes ask is, Mrs. Matthews, how do I know which way the arrows are pointing here? Do they point that way? Do they point down? Do they point up? How do I know? Imagine you're crossing the field at an angle. You're just walking diagonally across the field. Your friend is going to stick to the edges of the field. If you want to meet up, your friend has to go this way and then this way. So as long as your components lead you to the same endpoint as the original, then you've drawn your arrows correctly. So in this case, the y is going to be upward, and the x is going to be to the right, and that makes sense because my force is upward and to the right. Okay, now let's go ahead and use those two equations that I just showed you. Opposite equals the hypotenuse times the sine of the angle, and adjacent equals hypotenuse times the cosine of the angle. Oops. Look at that. Mrs. Matthews made a mistake. That should be cosine of the angle. Some of you probably caught that. Actually, some of you were probably asleep through that. Let's be honest. Okay. These are the correct formulas. So let's go ahead and plow into this. I just have to substitute. So the opposite, in this case, that's the y. So there's my y. is equal to the hypotenuse, well, that's 50 pounds, times the sine of my angle, which is 30 degrees. So in your calculator, you are going to type in 50 times the sine of 30. And if you get 25, then your calculator is in the correct mode. If you get something goofy, and let me put my calculator into radian mode for a second. If you get this goofy number, then your calculator is in the wrong mode. So your calculator needs to be in degree mode. So make sure that if there's a selection somewhere on there that says mode, please make sure that you are in degrees and not in radians. You can always Google help for your particular calculator to figure that out. So when I do 50 times the sine of 30, I should get 25. And that means that my y, my upward force, is 25 pounds. Let's do the exact same thing to find x. X is going to be my hypotenuse, 50 pounds, times the cosine of 30 degrees. All right, I'm going to type in 50, multiply it times the cosine of 30, and I get this kind of crazy long repeating decimal. Let's round that to 43.3 pounds. And that is how much of my pull is upward and how much of my pull is to the right. And that was the point of this exercise, to take a look at that slanty force and say that if I tug at a 30-degree angle with 50 pounds of force, I'm actually pulling it both sideways with 43.3 pounds of force and upward with 25 pounds of force. And for those of you who think, wow, Mrs. Matthews, your math is not mathing because 25 plus 43.3 does not equal 50. Unfortunately, with vectors, it does. And that's why we had to use these crazy trig functions to find that out. So that is how you will be able to find the sideways and vertical components of any vector of your choosing. So if I were you, I would make sure I understood this part pretty good. And in this case, the y is opposite and the x is adjacent, but be careful because if I was given this angle, it would be the other way around. So make sure that you pay attention to that. And that'll do it. Thanks so much for tuning in.